Lincoln algorithm can be solved very efficiently on parallel architectures such as GPUs. And so recall that we want to maximize the Wasserstein distance of Px and Pxc prime over the sum of Wasserstein distances, right? Pairwise, you're doing this pairwise, and sum over all, and here sum over all C and C prime. And so because the Wasserstein distance between mu and nu, here we have discretized it between matrix X and Z, and by definition, because we have defined is T lambda and M of X's and Z, so let's just substitute that and note that Pi transpose Pj is 0 if I is not J. And so P belongs to this Stiefel manifold that I just mentioned. And when I is J, P transpose P is 1. And the other thing you need to use in this substitution is that the inner product of two matrices is just trace of A transpose B. And so by substituting that, let's just substitute it together. The sum of T, so instead of this Wasserstein, you put this. T and M of Pxc prime, the inner product of this divided by, now for class C only, within classes, M Pxc and Pxc prime. And recall that M of X and Z by definition is just xi minus zj squared, but ijth component of that. So using that, you will notice that this is equal to maximize sigma over T. So just substitute that, nothing. Let's do it step by step. Zj, and now this xi is Pxc and zj is Pxc prime, divided by the denominator, and this is maximize of T, and I said by substituting that, it means that Pxc prime squared divided by denominator. But what we are doing is, this is the norm, okay? So the norm, the L2 norm of anything, such as F, can be written as and F and F transpose F. So using this in here, I will show you that you can write this as maximize T and Pxc minus Pxc prime transpose. So multiplication of these two vectors instead of just the norm. Pxc minus Pxc prime divided by the denominator. One more time, I can write, because AB transpose becomes B transpose A transpose, of course, it's like inverse, B inverse, A inverse. So using these notes, Using this, I can write this as sigma T and XC transpose P transpose minus XC transpose P transpose PXC minus PXC prime divided by denominator. And this is exactly this one that is written in the paper, the original paper. But so this sum goes into these CB and CW. So you know that CB is C and C prime, C of CC prime, and C of W is sum of C and C. So C and C prime, which is the general one, if you know this, then the rest of that is just special case. So C prime is the sum over I and J, TCC prime, I and J, XIC minus XJC prime, XIC minus XJC prime, for any C and C prime. So it's a bi-level optimization. I mean, it's a bi-level optimization. It is coupled, you know. On one hand, you are maximizing P and T of P, which we prove together it's maximized of P transpose P and CB, and P transpose P and CW. But subject to another optimization problem, which is T of P is equal to arg mean of E of T and P, which is equal to arg mean of sum of lambda T and M minus this entropy term, and we solve it using just the gradient descent. So it's so easy, and we can write the J as so J, P, T, and P that we want to maximize is P transpose P, CB. We are just rewriting it so that you see it. So the gradient, because you want to use the gradient descent, of course the projected gradient descent, because sometimes it goes out of the Stiefel manifold, we want to project it back to the Stiefel manifold. So the gradient of J with respect to P of P and T of P is equal to differentiate this Jacobian, this J, P of T, plus sum of J of P of T. You know, simple chain rule, no big deal, mathematics. And this one is, you can prove that this is P sigma 2 CB minus 2 sigma B2 sigma omega 4, some methy things here, and CW2 is just the inner product of CW, and CB2 is the inner product of CB. So that term is easy. This term for this term, I can separate the classes so that this derivative with respect to t, this is not equal to c. This is, we vectorize it as well. 1 over sigma wt m pxc and pxc prime, and we are separating them. So for C and C, this is minus vector of sigma b2 sigma w4 m pxc and pxc. So the last term that we need to know, this hard term, this one is really hard, because we have to solve it using automatic differentiation, because it is not available in closed form. And summing all these terms, we get this. And now we are ready for projected gradient descent for solving that. So we require, first you need to projection on Stiefel manifold. Stiefel manifold. You know, Stiefel manifold is just those matrices that we are interested to find. And so we initialize with k is equal to 0 and p0, and then we repeat the algorithm. The algorithm is that compute t c of c prime, and t of p is equal to arg mean of lambda t c c prime m pxc and pxc prime minus the that entropy term, which is tcc prime. So we use algorithm, we use that Sinkhorn algorithm that I said it is very fast and scalable to get t. So after solving that algorithm, that Sinkhorn algorithm, we have everything. It means that we can compute CB and CW, we can compute this gradient that we calculated. So at stage K, at the step K, we have PK and TPK. It is an iterative algorithm. So the gradient at this step is JK. And because it is a descent direction, you write it like this: projection over on Stiefel manifold of PK minus G minus PK. And of course, you need to do a line search if you are worried about your step size, and you should be worried about, because the step size matters, unless it is a very good and highly convex function. But still, you need line search, either exact line search or backtracking. Any kind of line search is okay. But pk plus 1 is now the projection of pk plus alpha k dk. And this is the direction of your projected gradient descent. And the reason that I write it like this is because if there is no projection, it becomes G. But since G is not in the Stiefel manifold, so pk minus G is not in Stiefel manifold. So we project it back to our Stiefel manifold. And after repeating this process, repeating it, k is equal to 0, and it converges to a solution. And it means that you have found the optimal P, this matrix, that reduces your dimension. You can enjoy your classifier. And so the algorithm is therefore complete.